What makes a tornado so powerful? At its core, a tornado is nature's most efficient way of transferring energy from the atmosphere to the ground. It forms when warm, moist air near the surface collides with cold, dry air aloft, creating instability. When this is combined with strong wind shear, meaning winds blowing at different speeds and directions at different altitudes, it sets up a horizontal rotation in the atmosphere. If a thunderstorm's powerful updraft, known as a mesocyclone, tilts that horizontal rotation vertically, a tornado can form. Once it touches down, it becomes a self-sustaining system that draws energy from the storm's warm, humid air. That fuel keeps it spinning faster and tighter until something, usually terrain, cooler air, or loss of moisture, cuts off its supply. The physics behind tornado strength. Tornadoes operate on the same physics as an ice skater pulling in their arms during a spin. When air is drawn inward toward the tornado's center, angular momentum causes the rotation to speed up dramatically. The smaller and tighter the vortex becomes, the faster it spins. In extreme cases, wind speeds can exceed 300 miles per hour, strong enough to strip asphalt off roads or debark trees. Scientists have estimated that a violent tornado can contain as much rotational energy as several atomic bombs, although that energy is concentrated in a much smaller area. Measuring tornado power, the enhanced Fujita scale. Unlike hurricanes, which are measured by wind speed, tornadoes are rated after the fact based on the damage they cause. This is done using the enhanced Fujita scale, EF scale. It ranges from EF0 to EF5. EF0, 65 to 85 F, minor damage, like broken branches or roof shingles. EF1, 86 to 110 F, roofs peeled off, windows broken, cars push. EF2, 111 to 135 F, mobile homes destroyed, trees uprooted. EF3, 136 to 165 F, entire houses leveled, trains overturned. EF4, 166 to 200 F, well-built homes destroyed, cars thrown hundreds of yards. EF5, over 200 miles per hour. Incredible destruction, entire neighborhoods flattened, concrete foundations swept clean. An EF5 tornado is the upper limit of what our atmosphere can produce naturally, and they represent less than 1% of all tornadoes, yet they cause the majority of tornado-related deaths. The role of pressure and suction. Tornadoes aren't just destructive because of wind. The air pressure inside a tornado's core can be dramatically lower than the air around it. In some cases, the pressure difference can exceed 100 millibars, roughly equal to the difference between sea level and the top of a small mountain. This creates intense suction. Where the pressure suddenly drops, buildings can literally explode outward as the higher indoor air pressure forces walls apart. Combined with winds that can pick up debris moving faster than 200 miles per hour, the result is catastrophic. How wide tornadoes can get. Not all tornadoes are narrow funnels. Some are more than 2 miles wide, covering massive swaths of land. The widest ever recorded was the El Reno tornado in Oklahoma in 2013, measuring an incredible 2.6 miles across. Despite its size, El Reno's wind speeds were complex, with multiple smaller vortices spinning inside the central funnel. These satellite vortices can cause extreme localized damage, which is why one side of a neighborhood may be wiped out while another remains standing. Tornado energy compared to other natural disasters. While tornadoes are relatively small in scale compared to hurricanes or earthquakes, the energy density inside them is unmatched. A powerful EF5 tornado packs energy comparable to a multi-megaton bomb, but that energy is focused over just a few square miles. To put it in perspective, an enormous hurricane releases more total energy, but it's spread across thousands of miles. A tornado, on the other hand, can destroy everything in a direct path, only a few hundred yards wide, but with 10 times the force per square foot. This concentrated destruction is what makes tornadoes so uniquely deadly and visually shocking. How scientists study tornado power. Meteorologists use several tools to understand tornado intensity. Mobile Doppler radars can drive close to storms and measure wind speeds inside the funnel. These radars have recorded winds over 300 miles per hour, confirming that tornadoes are among the fastest-moving air masses on Earth. Researchers also use damage surveys, drone footage, and computer models to reconstruct how the storm behaved. Every new storm adds data that helps scientists improve forecasting and warning systems. Despite decades of study, though, predicting exactly when and where a tornado will touch down remains one of meteorology's toughest challenges. The power of the updraft. A tornado's strength starts with its parent thunderstorm, particularly the updraft, the column of rising air that feeds it. In a supercell, the updraft can reach speeds of over 150 miles per hour. This immense upward motion helps create the rotating column that becomes the tornado. The stronger the updraft, the stronger the tornado can become. Some storms are so powerful that they can lift debris tens of thousands of feet into the atmosphere and deposit it miles away. There have been cases where photos, receipts, and even furniture were carried over 100 miles and later found intact. What happens when a tornado hits a city? When tornadoes strike urban areas, their power is magnified by man-made structures. Buildings channel and redirect airflow, sometimes increasing local wind speeds. Debris from broken structures becomes airborne missiles that can pierce walls or vehicles. In cities like Joplin, Missouri, 2011, or Moore, Oklahoma, 2013, EF5 tornadoes turned entire neighborhoods into rubble in minutes. Concrete, steel, and glass offered little resistance against the raw power of rotating wind. The mystery of tornado cores. Inside a tornado's funnel lies one of nature's most mysterious environments. Air pressure drops sharply, and winds spiral upward in a tight vortex. The core may be calm compared to the violent winds around it, similar to the eye of a hurricane, but the boundary between the two is deadly. Scientists can't safely place instruments in that exact zone, but computer models suggest temperatures may rise due to friction, and microbursts of lightning can even occur inside the funnel. Despite advanced technology, much about a tornado's interior still remains unknown. Tornado lifespan and energy release. Most tornadoes last less than 10 minutes, but the energy they unleash in that short time is enormous. A typical EF3 tornado releases around 10-15 joules of energy, equivalent to about 240 tons of TNT. Even smaller EF1 tornadoes can uproot trees and damage buildings, showing that even moderate-strength vortices carry immense destructive potential. Large outbreaks, like the 2011 super outbreak, can produce dozens of tornadoes in a single day, releasing energy equivalent to a small nuclear arsenal. What determines when a tornado weakens? Eventually, every tornado runs out of fuel. When its supply of warm, moist air is cut off, either because the storm moves into cooler air or merges with another system, the rotation begins to break down. As the funnel widens and slows, it often lifts back into the cloud, marking the end of its life cycle. But even as it dies, residual winds and debris can still cause serious damage. Understanding this decay process helps meteorologists issue all-clear warnings more accurately. How climate change might affect tornado power. Scientists are still studying how a warming planet could influence tornadoes. While there's no clear evidence that tornadoes are becoming stronger, there is evidence that tornado outbreaks, days with multiple tornadoes, are becoming more frequent. A warmer atmosphere holds more moisture, creating more instability. If wind shear conditions align, this could mean more intense supercells capable of producing violent tornadoes. The geography of tornado risk may also shift eastward in the United States, putting more populated areas at risk. Tornado myths about power. Many people think large tornadoes are always the strongest, but that's not true. Some small, rope-like tornadoes have wind speeds over 200 miles per hour, while some large wedge tornadoes are less intense. Size doesn't always equal strength. Another myth is that opening windows will equalize pressure and save your house. It won't. The winds and debris do the real damage, not the pressure difference. The safest move is always to get low and cover up, preferably in a basement or interior room.